Greetings and welcome back. Today we'll be looking at the reactions of acid chlorides. These are also sometimes called acyl chlorides. But this is a new functional group by us. It looks like this. It has a C double bond O followed by a Cl. So previously we looked at the reactions of ketones and aldehydes. Ketones and aldehydes are both really reactive at that C, which is attached to the oxygen. Because the oxygen is more electronegative, it's pulling electrons away from it like this. But how much more so in an acid chloride is that carbon going to be electronegative? Because it not only has the oxygen pulling electrons away, but it also has the chlorine pulling the electrons away. So if the carbon in a ketone is electrophilic, and the carbon in an aldehyde is even slightly more electrophilic, the carbon in an acid chloride is exceedingly electrophilic. So what we'll do today is I will first show you the general reaction by which acid chlorides react with nucleophiles, and then we'll look at some other similar functional groups to acid chlorides, and then we'll get into specific reactions of acid chlorides. So we're going to start off with a general reaction by which an acid chloride would react. So remember that we have that chlorine right there attached to the carbon and the oxygen attached to the carbon, and therefore that carbon will be very, very electrophilic. So we will react it with a nucleophile. The nucleophile in this case does not need to be strong because the electrophile is plenty strong enough, but that's okay. We'll just use a generic nucleophile that's negatively charged to make sure this gets done. So let's attack with the nucleophile. It's going to attack that carbon, and as you can probably tell, there's two things that can happen. Either you can kick the chlorine directly off, or you can kick electrons up to the O. That carbon effectively has two leaving groups attached. But there is no choice here. The only time you can do an SN2 reaction, which involves kicking the leaving group directly off, is if you have an sp3 carbon. That is to say, a carbon making 4 single bonds. Since this carbon is not making 4 single bonds, it cannot do that, and instead, it must proceed to kick electrons up to that O. So that would give us an intermediate that looked like this. It would have an O- up here. It would still be attached to the chlorine, and it would now have a new bond to our nucleophile. So that's my new bond right here. I'll color it in green for you right there. All right. Well, at this point, I've gone from a nucleophile with a minus charge to an oxygen with a minus charge. But what this molecule would really like to have is a chlorine with a minus charge. And so what will happen is that these electrons come back down, and when they do, that would make a fifth bond to that central carbon, so it would have to kick something off. And in this case, we can go ahead and kick that chlorine off. So the final product over here would be that I would now have my R attached to my C double bond O. I've remade my carbonyl. And now I have the nucleophile attached over here. I'll just write that out all the way in green. And I've kicked off my chlorine as a leaving group, so I have a Cl-. As you can tell and as you can imagine, chlorine is one of the most stable negative charges we have. Therefore, the overall reaction energy diagram for this would be we'll start here, and it will definitely go up in energy to get to that tetrahedral intermediate, because that thing is negatively charged and it's got all 4 bonds attached to that carbon. It's got a chlorine and an oxygen, so that guy's a little bit of a disaster. And then a much easier reaction is the second one, in which we kick off the leaving group, so not much activation energy there. We go down in energy for sure to get to that product. So this is the general reaction of an acid chloride. You attack with a nucleophile, kick electrons to the O, they come back down like this and kick the leaving group off. So I like to think of this as a bit of a slingshot. First, you charge it, you push electrons up to the O, they come back down again and kick a leaving group off. All right, and this is called sometimes addition-elimination. So it overall looks like a substitution reaction, but in the first step, we performed addition, and in the second step, we performed elimination. So overall, this reaction is referred to as an addition-elimination reaction. All right, so let's look at some examples of other molecules that react like acid chlorides. So other molecules that react like acid chlorides are impacted by what we have in place of that halogen. So this is an acid chloride right here. It's got the C double bond O and the Cl. But other molecules can react in similar ways depending on the nature of that leaving group over there on the right. So compared to that guy, let's just think about leaving groups in general. So this is a flashback to last semester. Leaving groups are things that can leave and become more stable after they've left. So we talked a lot about this when we talked about stability of ions. So with leaving groups in general, we had the sulfonyl group, which was this SO with whatever. I'll put an R here, an R prime, so something else. So this, for example, we had OTS. There is O-mesyl and O-triflyl, which was the trifluoromethyl. So any of those do, but they have that sulfonyl up there. Those are more reactive than the RBr, which is more reactive than RCl, and in both of those cases, the leaving group would be Cl minus or Br minus, which is really stable. In the case of these guys, you'll have that O minus attached to an S double bond O with whatever attached. That's really stabilized through resonance. And then after that, what we would have, and those are the main leaving groups that we've talked about. You could also have this guy, right? And if that guy left, what you would get would be an O minus with 2 resonance structures as opposed to 3 resonance structures like in the sulfonyl. And beyond that, we have fluorine. I've kind of run out of space. Fluorine, which is okay but not so good. And then we have kind of OR, which is really not that great of a leaving group whatsoever. And alcohol, which is also not a very good leaving group. So where we are right now when we talk about acid chlorides is we're right in here. Chlorine's a really good leaving group. A Br is kind of similar in terms of that. We don't have a C double bond O attached to a sulfonyl. So pretty much where we are right now is the best leaving group overall. So we have another number of other functional groups similar to this, but they tend to be or have less reactivity. So the next one that we will see pretty often is an anhydride. An anhydride would look like this. The leaving group would be this part right here, which, as we noted, is pretty close to chlorine. It's a little bit less reactive than chlorine, but it's still a pretty good leaving group. We don't ever have fluorines on there, but after that, the reactivity really drops off. So similarly, we could have esters, which look like this. Their leaving group would be OR, so kind of an O minus. That's not very good. Below that, we would have OH, which is also not a very good leaving group. And finally, below that, we would have amides. Amides would have an N leaving group. And compared to what we had over here, an N is an even worse leaving group. We'll just put H2, but it could be 2 R groups. Because if you think about the leaving groups for these guys, the leaving groups for these guys would be an F minus, which is okay, or an OR minus, which is an O minus, which is getting pretty unstable, an OH minus, which is also pretty unstable. Furthermore, get down to an N minus, and N minus is really unstable. We almost never see an N minus. So these guys at the top here, the acid chloride and the anhydride, these guys have really good leaving groups, and therefore they will react pretty readily with any nucleophile. The ones below them are not nearly as reactive. So the 2 that I've circled up there, we're going to cover those in the next slide in terms of specific reactions. These guys down at the bottom, we'll look a little bit more closely at those in the next video. So what I've drawn here is 3 different reactions of acid chlorides. One in which the acid chloride reacts with water, and the second one with an alcohol, and the third with an amine. Let's walk through together that first reaction, and then I'm going to ask you to try to figure out the second and the third. So, following our general mechanism, we have a nucleophile, that is the water, attacking this really strong electrophile right here. Again, because this electrophile is so strong, we don't need an incredibly strong nucleophile to get the job done. So, our nucleophile will share its electrons and attack the carbon in the carbonyl, It kicks electrons up to the O, which would go up in energy, but we're going to kind of shortcut this mechanism a little bit because we know that the electrons come back down and kick the chlorine off. That would give us a product that would look like this. We would still have all of this stuff, but now instead of having the chlorine attached, I would have an OH2+. The chlorine will have come off and is just hanging out. So if you have water, you have plenty of water hanging around. So you have this kind of second step in which the water can act like a base, do deprotonation. Deprotonation is something we've seen a lot already. If you have an extra hydrogen, you can just pull it off of the base, and that would give us a final product that looks like this. Overall, what we've done is we've started with an acid chloride, and this would also work with an anhydride, as seen in the previous page. Anhydrides will do any of these same reactions, and it will convert it overall to a carboxylic acid. So this is a really easy reaction by which we can convert an acid chloride into a carboxylic acid. So acid chlorides are great. They have tons of reactivity. So what I'd like you to do is take a second and pause this and try to do the second reaction as well as the third reaction and see what functional groups you get. All right, so let's walk through these reactions as well. The nucleophile that is the alcohol could attack that carbonyl, kick electrons to the O, which slingshot back again, and kick off the chlorine. So in that way, with our acid chloride, we would displace the chlorine and replace it with, in this case, an OH with 3 more carbons attached. That has a positively charged O with a hydrogen attached, so once again, we don't need to add in anything else, just more of that alcohol hanging around could do a deprotonation for us. We'd grab that H, and we would make a neutral molecule that would have all of that ester all over the place. So this is an ester right here. So we can also make an ester out of an acid chloride. Finally, in this third one, again, we're doing the exact same thing. Our nitrogen will attack, kick electrons up to that O. Oops, they slingshot back down again and kick off the chlorine. And now instead of the chlorine, I would have a nitrogen attached. So this whole part of the molecule remains the same, but instead of having the chlorine there, we'll have and with 2 H's, and it would still have that ethyl group. So once again, I have a positively charged species, and we need to deprotonate it. Thankfully, we have an amine, which amines are very readily basic already. And so one of those guys could just pull a hydrogen off of that guy, and that would give us the final product of the C double bond O attached to an N, which is an amide. These are by far the most often used ways to make esters and amides. So, acid chlorides are really wonderful, they're really helpful to us. How do we make acid chlorides, you might be asking? This incredibly useful but also incredibly reactive species? I am glad that you asked. So you may recall, in a similar reaction, if we want to make an alkyl chloride, or an RCl, we can make it from an alcohol using SOCl2, which is thionyl chloride. That guy will replace the OH with a Cl. And likewise, the best way to make an acid chloride, which has that Cl there, is from a carboxylic acid, which has an OH. And I tell you this because, again, the best reagent to use to do that is SOCl2. In both of these cases, the mechanism is the same. We're able to turn that OH into a better leaving group and then replace it with a chlorine. So you can try to do that mechanism if you'd like, but thionyl chloride is incredibly important to us for 2 different reactions. One is to make an acid chloride. You may hopefully notice and ask me, Dr. Ring, why would I want to turn an acid chloride into carboxylic acid when the best way to make an acid chloride is from a carboxylic acid? And I would say, good call. We don't usually do that top reaction because we use carboxylic acids to make acid chlorides. Therefore, turning acid chlorides back into carboxylic acids is awfully silly. All right, so let's jump into a couple more reactions and then we'll be done for the day. If you start with this acid chloride right here and add our strong nucleophiles, so we're getting into strong nucleophiles right now, let's go with, let's use the alkyl lithium, this guy right here. So I'd like you to try that mechanism and tell me what you get. All right, so this is a 2-carbon chunk that acts like a C-. So it acts as if it's this thing. And what it will do is just the same as all those other mechanisms. We'll attack that carbonyl, kick electrons up to the O, bring them back down again, and kick off the chlorine. And that would give us, boom, 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 a new bond to a 2-carbon chunk that would look like this. So what we've made is a ketone. But the reaction tends not to stop there because a ketone is still reactive. If you have any of that alkyl lithium hanging around, it's going to act like a C- again. And what that will do is once again attack that carbonyl, kick electrons up, and we would end up making something that looks like this. So this right here is the new stuff that we did for this video, that you can attack an acid chloride and regenerate your carbonyl. But this over here is the one that we did in that last video, that a strong carbon nucleophile can also attack a ketone or an aldehyde. So you can't stop those reactions from happening, and you end up kind of stuck. So therefore, acid chlorides will get attacked twice by a strong carbon nucleophile. All right, hopefully you don't fall for this again, but let's try this with a hydride. So let's try this with lithium aluminum hydride, LAH. I'm going to draw this guy out. It's Li plus, Al with 4 H's attached. So what this guy wants to do to make that negatively charged aluminum neutral is to push off an H, and therefore this guy acts as if it's H-. All right, so assuming we have lots of that stuff, see what you can do. All right, so once again we have an H-. I'll just write it in green. All that stuff up there acts as if it's just H-. And the H-, which is again a very strong nucleophile, will attack that carbon, kick electrons up to the O, which will come back down again and kick off the chlorine, and we will end up making C double bond O with a new bond to an H. But once again, if you've got a bunch of lithium aluminum hydride hanging out, you've got more H-, and H- will certainly attack an aldehyde or a ketone, but in this case an aldehyde. Kick electrons up there, and what we will have done in this case is attacked twice yet again. So in both of these cases, if you add a strong nucleophile, either an H- or a strong C-, we will end up attacking this guy twice. So to sum this up, acid chlorides are incredibly electrophilic, and a weak nucleophile will attack this guy and kick electrons up to the O, slingshot them back down again, and kick the chlorine off, which gives us a new bond from a C double bond O to some weak nucleophile. But if you start with this guy and you attack it with a strong nucleophile, which is usually negatively charged, what will happen is that you will do this once, and then you'll often have to do it 2 times. And the second time it will attack again. I wouldn't draw all these mechanisms together, but you end up having that strong nucleophile attached twice. So we need to be able to differentiate our strong nucleophiles from our weak nucleophiles in terms of this reaction. We will talk about some more examples in class, especially how we can attack with hydrogens and carbons that are weak nucleophiles and only add once. And that these are all very important reactions, especially in terms of making new carbon-carbon bonds, which lets us build bigger molecules. All right, thank you very much, and I will see you in class.